Okay, so where things left off last time, and I ended with the transition from working on a level sidewalk to working on a ramp. Just to remind you what the story was before we go into a ramp, is that something like the wagon here, maybe the wagon with the blocky kid in it, if the only force acting on it were gravity, were the force due to gravity, its weight in other words, it would fall. It would accelerate downward faster and faster and so on. The fact that it's not, that its acceleration is zero, that it is at equilibrium, means that something else is pushing on it, and thus something is the sidewalk, and the sidewalk happens to have figured out to push upward on the wagon with a force that's exactly equal in amount to the wagon's weight, but in the opposite direction. So the net force on the wagon is zero. I mean, when I do this, I'm thinking to be very logical. It's like presenting a case before the court, to prove it. That may be tedious to listen to. It's a little tedious to say it, but to an extent, it is what it is. That wagon's experiencing two forces. They happen to be exactly equal in amount, opposite in direction. They sum to zero. One of them is due to the sidewalk. Questions about those ideas? Those two forces, they sum to zero. The net force is zero. The thing's not accelerating. Again, I'll point out that when the net force is zero, the observation that tells you that is that the acceleration is zero, not that the velocity is zero. This wagon can move and still be at net force zero. There. When it's inertial, those are both it's got net force, well, not quite zero. It's very close to zero. It moves almost as inertia had in mind. Anyway, so you look for acceleration. If it's not there, all the forces are summing to zero. The force that's managing to keep the wagon from accelerating, that is from falling, is a support force. It's caused by the wheels and the sidewalk trying not to overlap in space. They fight each other, they push apart, and because they push apart, the support forces are always exactly perpendicular to the surfaces that exert them. The wheel and the sidewalk touch on a very horizontal pair of surfaces, and they push apart vertically. All right, so we're okay? What if we tilt the sidewalk into a ramp? If I do that, I'll do it having survived last class without killing myself, destroying the wagon, and so on. I'll be a little more careful this time. I haven't watched the video of my antics, but I survived. Okay, if I tilt the sidewalk and the only things pushing around are the support force of the sidewalk and the weight of the wagon, it accelerates. It seems to have developed some odd shape. All the collisions of yesterday, or the falls of yesterday, were not good for it. Okay, this wagon now, if you leave it alone and if I let go of it, it accelerates down the ramp. That's the observation. I hope you can see that. It starts at rest, and if I let go, it goes faster and faster downhill. It go right along the ramp, which means that its velocity is always right along the ramp, and it goes from no velocity to a little more down the ramp, to a little more, to a little more, to a little more, faster, faster. So observation alone tells us this guy is experiencing a down the ramp force, and therefore is accelerating down the ramp. Where does the force come from? It comes from the sum of two forces still. Just as before when the wagon was sitting on the horizontal sidewalk, the wagon was experiencing two forces, support force straight up, perpendicular to the horizontal sidewalk, and the weight straight down, as it always is. They canceled perfectly, no acceleration. Now, those two forces are still there. They don't cancel anymore. Why not? It's because the surface of the ramp is no longer horizontal. It's tilted. And the support force that exerts on the wagon is still perpendicular to its surface, but it's not vertical. It's at an angle. The support force that this ramp exerts on that wagon, I'll illustrate it with a stick. It's pointing in this direction, up and a little to the right. Well, if the wagon is experiencing two forces, one of them straight down due to gravity, and one of them up at an angle due to the support force from the ramp, those can't sum to zero. There's an angle problem to this. No matter how you adjust them, you can't get them to kill each other off. You can do it when they're vertical, but not when they're tilted. So if you do the vector sum of a force that's up and to the right, plus a force that is straight down, when you do that, and there are ways to do it graphically, and there are ways to do it with numbers on a sheet of paper, you end up with a leftover. And that leftover is the third arrow here. It's pointing perfectly along the ramp and downhill. And that, I call that force the ramp force. It is not a fundamental force the way gravity is, specifically due to one phenomenon in nature. It's the sum of two forces, each of which is fundamental. And so in this case, that ramp force, which is, in other words, the sum of the weight plus the support force, happens to have a small amount. It is not very strong. It's not nearly as strong as the weight of the wagon, but it points exactly along the ramp. And why does it point exactly along the ramp? Well, it's because the support force is still doing the negotiation trick. It's still obtaining the ramp and the wagon are pushing against each other, trying to figure out just how hard to push on each other so that they don't get any closer, and they also don't get any farther apart. If they were to get farther apart, the force that caused them to get farther apart would itself start to disappear. Because if they stop touching, there's no support force. So there's a negotiation going on, make sure the wagon is just sort of staying at the right distance from the ramp, no more, no less. And when that all happens, the support force develops just the right strength that when you add it to the weight, you get this downhill ramp force. Okay? Some news about the strength of that force. As I said, it's weaker than gravity. It varies with the steepness of the ramp. So, in fact, it varies beautifully smoothly from two extreme values, depending on the steepness. If I let the steepness go less and less, now the force is weaker and weaker. In fact, it's so weak, I'm barely getting any downhill acceleration. So the force is very weak. And if I go all the way to horizontal, the ramp stops being a ramp. It becomes a sidewalk. At that point, the two forces add to zero, and the ramp force goes away. So ramp force starts at zero when the ramp is not tilted, and as you tilt it, the ramp force gets stronger and stronger and stronger and stronger. And I'm not going to do this with a weight in there. I'll take the kid out, okay? It's stronger, 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 stronger. Whoa, all the way up here. Now the ramp force is the full weight of the wagon, and the wagon accelerates at the full acceleration due to gravity. So what the ramp is doing for us is it's allowing us to sort of exert a force on the wagon that resembles weight in the cockeyed direction, but goes from zero to a small fraction of the weight to a bigger fraction of the weight to bigger still to the full weight. You get the whole variety pack just by varying the steepness of the ramp. And you've hopefully experienced this, pushing, a grocery cart up the little shallow ramp, no problem. The steep ramp, whoa, this is harder. Okay, and so on. Any questions? Yeah. All right. If I push uphill on the wagon just hard enough to balance that downhill ramp force, so I am going to add a third force. Weight, support force, together they make ramp force, and my hand. What's going to happen to the wagon if I exactly balance the ramp force? You okay with the question? Questions about question? How many think that the wagon will be motionless? How many think that the wagon will have a constant velocity, which might be 0? Okay. The majority, the voting's a little thin. It's okay. It was probably 3 or 4 for 1 in favor of the constant velocity story. And that's the correct answer. Be motionless. Come back here. It needs 7 hands. Okay, to be motionless is a possibility. I'm pulling uphill now with a force that exactly balances the downhill ramp force. How do we know that? It's because there's no acceleration. It's the key measurements. Look for acceleration. So that's true. So B is a possibility. All right, A is a possibility, be motionless. But it's not the whole story. I'll show you another situation in which I'm exactly balancing the ramp force. Don't look yet. I have to get the story started. Now look. It's moving uphill at constant velocity. End of story. During that period when it was moving at constant velocity, it was also not accelerating. It had a velocity that's not 0, but that's okay. It was keeping it. So the net force on it was 0. It wasn't accelerating. So why do I even ask questions like this and then harangue on it? Is again to help you recognize that forces cause accelerations. They don't cause velocity. Velocity has a lot to do with what was the thing doing before the story started. So here's a case where if you manage to cancel all the forces on the wagon, the most you can say about it is it's moving steadily, constant velocity. You can't be sure it's motionless. That's a possibility, but not for sure. So any questions about the difference between those two observations? Why it matters? Okay, so if you want to get something to go uphill, so you want it to go up on the wagon, there are really 3 steps to the story of taking the kid up on the wagon. I'll put the kid back in. Always hazardous, but okay. So you're at the bottom of the ramp, and worrying about the transition from the sidewalk onto the ramp is just complication for no reason. So suppose I want to get the kid and the wagon from this point to this point. There are essentially 3 parts to the story. The first part is, well, I'm perfectly, this is actually before the story starts. I'm perfectly balancing the downhill ramp force. How do you know it? Again, the usual thing, it's not accelerating. Okay. If I want to get the wagon to the top of that ramp, I have to change something. We're going to be here all day. So I have to make the wagon accelerate up the hill. How do I do that? By pulling a little harder uphill than the ramp force pulls downhill. So the wagon experiences a net force uphill. Simple as that. I've got to start by pulling a little extra hard. So here we go. Ready? Extra hard, and now I've got it moving uphill. Now we're in the middle part of the story. Once I get the thing moving, and let me stop the story here, and let's just sort of, we'll freeze frame. Okay? It's still in the process of moving uphill, and it's moving steadily now. So the second part of the story is, I've already got the wagon moving uphill at the pace I like. How do I keep it moving uphill? All I have to do now is balance the downhill ramp force. I don't have to pull harder than it. I have to pull equal to it. When I do that, the 2 forces cancel. In other words, they sum to 0, and it goes steadily up the hill. Great, that's what I want. So to get started, to go back to part 1, to get started, you have to pull extra hard. To keep it going, you don't have to pull extra hard. Just pull enough to keep it going, to balance the downhill effects. And then finally, at the third part of the story is, we're getting to the top of the hill. I don't want it to keep going. I want to let it stop. How do I do that? Well, I pull a little less hard than the ramp force pull. I pull a little less hard uphill than the ramp force pulls downhill. I let the ramp force win. In that case, the ramp force causes the wagon to slow down. It's going uphill, velocity uphill, acceleration downhill. It loses its uphill velocity and comes to a stop. All right? So you do this all the time without really thinking about it. You got a ramp there, you've got something, you want to get up the ramp, you give it an extra big push to get it started up the ramp, then you keep balancing the downhill ramp force to keep it going, and at the end, you sort of back off and let it come to a stop. Can you, questions about this? Do you feel that those three stages? Can you sort of, in your mind's eye, imagine them and feel yourself doing it? Yeah, Nico. Yep. Okay, so Nico's question is in the middle territory, it seems puzzling that the forces are balancing one another. Uphill is the same in strength as downhill, to sum to zero, and yet it's still moving, right? And this is as you observe, this is a struggle to disentangle velocity from acceleration. Those two forces summing together to nothing affect acceleration of the wagon. They don't affect the velocity of the wagon. The velocity of the wagon has to do with what was it doing a moment earlier. Particularly when you've got no acceleration, that means its velocity a little bit in the future is going to be the same as it was a little in the past. So the crucial issue is what was it doing in the past? And it was heading uphill in the past. So this moment when it's not having any acceleration, no net force, means it's allowed to continue doing what it was doing, which is moving uphill. Is that helping? You got that idea, guys? Everybody? Yeah, so if you watch stuff, and I do encourage you to watch stuff, one of your fellow students was riding a bicycle and had a bicycle accident recently, which is a sort of side issue, but don't watch stuff when you're in a jeopardy, a situation where watching too much is dangerous. But watch people bicycling, not yourself, other people. And as you're moving along, as you're watching them move along, when they're moving steadily, straight and true, it's not because something is pushing them. It's because nothing is stopping them. The net force on them is zero. They're moving the way inertia had in mind. It doesn't require a force to move. It requires a force to change your movement. Is that okay? It is not intuitive because I think I've done this already with you all in class here, but it's just to remind you, you have so many experiences where if you don't push it, it stops. And if you do push it, it moves. Don't push it, it stops. You think, well, forces cause velocity. That's your everyday experience. Forces cause speed. Well, that's not right because you're not the only force acting on this gadget here. Friction's there too. The table is pushing on it, and it's fighting you in a sort of a clever way that causes it to stop whenever you let go. Friction's not literally smart, but it behaves in a way that brings things to the same velocity whenever possible. In this case, the table has a velocity of zero. The sliding scale has a velocity that's not zero. The two are fighting to agree on a velocity, and the table wins. They end up at the same velocity, zero. But that's because of friction. So if we could get rid of friction, and that was the point of having the skater on ice or on wheels or something, get rid of all the friction effects. Get rid of air resistance and stuff. I mean, the ideal thing would be a skater in deep space. Taking the skater to the moon, getting rid of air resistance would be great, but then the skater would have to have scuba gear. In any case, get rid of the friction, get rid of the gravity, get rid of all. Life is simple. If you bring in friction, it gets complicated. But I'm trying to help you see what life would be like in the absence of these nuisances. All right? All right. Why is it harder to lift a wagon up than lower a wagon down? In both of these cases, so these are, we'll look at the middle part of the story in two cases. One is the story hasn't even started yet. The first part of the story is acceleration. Second part is steady motion. Ooh, okay? Third part is slowing down. In that middle ground, heading up, it was coasting, and I was pulling up. And if you're doing this, if you are responsible for pulling the wagon up and the wagon's full of kids and stuff like that, you get kind of tired doing this. All right? There's a second version of the story that's almost very similar. I'm going to show you the second version of the story. It hasn't started yet. And it starts with accelerate downhill, then coast, then accelerate uphill to bring it to rest. It's the same kind of story. At the beginning and the end, you unbalance the forces on the wagon so that it accelerates. In this case, though, you unbalance them so it accelerates downhill at first, and you accelerate them, you unbalance them so it accelerates uphill at the end to come to a stop. The difference, though, I should say, I'll repeat myself for the 8,000th time. Any questions? All right. I do appreciate the questions when they happen, for real, okay? Otherwise, again, I could just tape myself doing it right once, which is tough, get it really clean, play it back every year. I could sit in the audience and play with text messages. These two versions of the story, one in which you get it moving uphill and then coasting, and the other in which you get it moving downhill and get coasting, physics is sort of indifferent to them. They both work perfectly. The laws of motion all work out nicely, no problems. But there is the experience when you do this that it is more exhausting going up the hill than it is going down the hill. You're doing something different in the process of these two different motions. I hope these are all experiences that are familiar. If pushing a wagon up and down a hill doesn't resonate, think about walking up and down a hill. When you walk up a hill, you're the wagon. You get yourself moving up the hill. You instantly do that by getting a strong uphill force. How do you get it? You use your feet and friction to grip the road and have the road push you up, or the sidewalk the ramp push you up the hill. So you're getting an uphill force from the pavement. It's a frictional force, which is in our future, but anyway, so as you walk up the hill, you know it's more tiring going up the hill than it is going down the hill. You feel it. Something's happening here. And a way of looking at the difference is in terms of a quantity known as energy. So this is my excuse or a reason to bring up energy. And we'll see more that it's really interwoven in the story of a ramp. Energy, what's energy? Energy is the first of four conserved quantities that will come up this semester. The fourth one being electric charge. We'll see that's off beyond the horizon at the moment. Energy is a conserved quantity. And a conserved quantity in the world of physics is a quantity that cannot be created or destroyed, that is a certain amount, and it can move around or change forms, but you can't make it or destroy it. And my analogy to a physical quantity that's conserved is a financial quantity that's conserved, money. So in a society that follows the rules and setting aside high finance, money is basically a conserved quantity. It moves around between people. It may change form. Sometimes it's nickels and dimes. Sometimes it's dollar bills and so on. But it is the net amount of money in a community that's isolated on a desert island, say, the net amount of money isn't going to change. It's just going to move from place to place and do things. And often the transactions that move money, spending, earning, they're interesting. They make things happen. The same thing happens with energy. Energy is one of these conserved quantities that in a sort of the physics version of a desert island, an isolated planet that doesn't interact with the rest of the universe. The energy is conserved. If there's a certain amount there, it's going to be there tomorrow. But it can move around between parts, and the moving is interesting. So as it goes from one person to the next, or from a person into a box, or out of a box into a person, so it matters. And watching it move gives you a lot of insight into what's going on in the system. What else about it? It is sort of technically defined as the capacity to do work. Okay, well, so that's fine. What's work? Work is the mechanical means of transferring energy. Well, that's very circular. That says that energy is the capacity to do work, and work is the movement of energy. What is it? To use my financial analogy, that's like money is the capacity to spend. What's spending? It is the transfer of money, all right? But still, money allows things to happen, and the transfers particularly are sort of causing the happening. The same thing with energy. Energy is the capacity to do work, and the doing of work causes things to happen. So it's interesting. The circular definition isn't a problem. It works out okay. It happens that energy is conserved. It comes about because of some of the fundamental laws in part of motion. And if you look at the mathematical structure of how velocities change when you exert forces and so on like that, it all creates a self-consistent situation in which there are a couple, and this is one example, there are a couple of conserved quantities that arise because of how the laws of motion all work, the Newton's laws and so on. And one of them is this energy. Energy, incidentally, it's called a scalar quantity, meaning that it's not a vector. It does not have a direction. I'm going to have some energy in the moment associated with my rightward movement. End of story. I now have the same energy associated with my leftward movement. The direction of my movement didn't matter. The fact that I'm moving and how fast I'm moving and how much mass I have moving, that's where the energy is. There's no direction to it. Is that okay? Okay, so how do you do work? So energy is something you can have. So I have a certain amount. I didn't create it. I brought it in from elsewhere. Eating food brings energy into me. With that food energy now, I can do other things. I can do work on the world around me. And in doing so, I give away some of the energy that I ate earlier. So how do you give it away? How do you do work? And I should say, work is the mechanical means for transferring energy. That is, it's the way you do it by way of forces. There is one other way in which you can transfer energy that I deal with in the other semester, the fall semester, and that is the thermal means for transferring energy. The thermal means of transferring energy is called heat. So you give heat to something, you touch with your hand a cold object, an ice cube. Energy moves from you to the ice cube, not by work, but by heat. Heat actually is secretly is little tiny bits of work. So it's still the same stuff. But the point is that just for your own reference, the word mechanical is in there because there is a second way to transfer energy, and it's thermal. Not part of our story today, this semester much. Okay, so work, mechanical means of transferring energy. How do you do work on something? The rules are very simple, and they're narrowly focused. Yet to do work on something, for example, the bowling ball, which is always my example, I'm going to get lazy. Up and down like this with the bowling ball. I feel it too much, okay? So, the rules for doing work on the basketball. You got to push on it. So if I'm not pushing on the basketball, I cannot do work on it. I cannot transfer my energy into it. Now I got a chance. You got to exert a force on it. In this case, my force is upward. I hope that follows pretty easily. You know, if you were holding the basketball, you would be pushing it upward. You all can see that this is the case because it's not accelerating. When you know it's got a weight, I had better be canceling the weight. So I'm pushing up, okay? So I'm pushing up on it. That's part one. And the other part of doing work is it has to move a distance in the direction of my force. My force is up. It has to move somewhat upward, like that. I just did work on it. Nothing else matters. You know, what's under my feet doesn't matter. I can do work on it like this, or I can be in an elevator and do work on it like this. Right? It doesn't have to actually, the work doesn't really have to come out of me. It can go through me. The elevator can do work on me, and I can do work on the ball. Doesn't matter. The issue is, am I doing work on the ball? Just look right here, narrow focus. My force on the ball is up, and the ball's movement is up. Hey, we win. Work done. Okay? So this is work done on the ball. You okay with that idea? And you might think, well, okay, so this was just like following the rules and the recipe, okay, it did it. What, was energy really transferred? Is there any there? And the answer is yes. In doing this, I truly lost energy. I can't do this without having consumed some food somewhere along the line. I needed energy in because I'm giving it away. The ball now has that energy. It is now able to do things it could not do before. For example, if let me do the whole 9 yards. I'll start at the bottom and then I go all the way up with the sound effects and everything. The ball could do things like that it couldn't do when it was down here. If I let go of it down here, it's boring. Okay? So I increased its capacity to do work, to do interesting things, to get things done by doing work on it. It truly changed. All right? So in watching the movement of energy, there are actually two conceptual ways to see it. One is to actually watch the work being done. I'm pushing up on it, it's moving up. I'm pushing up, it's moving up. I'm pushing up, it's moving up. We're watching the work happen. The other thing is the other way to do it is look at the before and after. So look now, and close your eyes in principle. You can look, that's okay. Okay, you look now, secretly. Okay. Now look, I changed its situation. It used to be down there, now it's up there. It can do things it couldn't do before. That means somebody did work on it, added energy to it, and in all likelihood, it was me. Okay? The financial equivalent is again instructive. I hope you will find it useful. The financial equivalent is two people, Alice and Bob. Bob's got no money. Alice has $10. So Alice hands $1 to Bob, $2 to Bob, is spending, is giving the money to Bob. And you can watch the money move by looking at it moving, the bills going from one hand to the other. That's like watching the work being done. The alternative is, here's Alice with $10 and Bob with 0. And close your eyes. We don't know what happened. And now suddenly Alice has got no money and Bob's got $10. The money must have moved. Where did it, what's the most likely situation? Well, probably Alice gave the money to Bob. Okay, before and after. All right. Some of this stuff is sort of, even to me, it seems kind of like pedantic. But we'll see that there's value to having these various perspectives on how stuff goes on. And when we get into complicated things like how electric power goes and moves into your house and gets things going, it all building on that sort of story. Okay, so this is the story of work, doing work. It brings up other issues like, well, if this is doing work, what is this? And what it actually is, for me, when I do this, I'm doing work on the ball, I'm adding energy to it. When I do this to the ball, I'm doing a negative amount of work on it. And I'm sucking the energy out of it. And it's going back to where it started. I took the energy back. And a little bit about language. This is doing work, and this is doing negative work. And a word that I'm not using, and I could, is this is positive work, and this is negative work. So why do I say just work? Why don't I always say positive? Well, because it's wordy. And because there is a convention made, certainly among physicists, but more broadly, that we say that positive is the standard. If I don't say negative, I'm talking about the positive stuff, a positive amount. This is work. So I don't need to say positive, it's assumed. For those of you from 1050, it's the same joke. When you give money to charity, we assume it's a positive amount of money. Only a real heel would give a negative amount of money to charity. You can do it. Instead of giving them your stock certificates, you give them your mortgage. Suddenly, they have more debt, right? So this is work. I don't have to say positive, it's assumed. that okay? So it's also instructive to look at the full transaction. And let me set it up by playing Alice and Bob. Alice and Bob show up in quantum information theory all the time, which is not my field, but it's always Alice and Bob. Anyhow, and I killed my own train of thought. Full transaction. When Alice gives $10 to Bob, that's half the transaction. Alice is losing $10. Oh, right. Bob is the other side of the transaction and is receiving the $10. And that's the second side of the transaction. You needed both of them. And money is conserved because the amount that Bob receives is the same as Alice gives. And that may seem completely obvious, but it's there. And the reverse transaction works the same way. So when I do this, when I lift up, I am transferring, say, 10 units of energy, and I'll name the units in a minute, to the ball. That's half the transaction. What happened to me? The ball, we know the ball received 10 units because I did it. What happened to me? Well, the ball, which way is the ball pushing on me? Show me with your hands. Down, right? Which way am I moving when we do this? Up. Ooh, those are in opposite directions. The ball is doing negative work on me. How much? 10 units. So I'm giving it 10 units, and it is giving me negative 10 units. It's on the way up. I should be careful what I do. So the transaction is complete. I gave it a certain amount of energy, and it took exactly that same amount of energy out of me. And this, what underlies this? Well, what underlies this is Newton's third law. I push up on the ball with a force equal to the force that the ball exerts, equal amount to the force the ball exerts on me. So, and we travel the same distance. So the amount of work that I do on it, namely 10 units, is exactly equal to the amount of negative work it does on me. Exactly balanced because of Newton's third law, because of the two distances are the same. It all perfectly works out. If Newton's third law weren't true, energy wouldn't be conserved. If it didn't push on me at all, I could do work on it and it would do nothing on me. We'd make energy out of nothing. And we could go sell it on the internet. And people do all the time. There are lots of this stuff around there. It's fun to watch. Genesis? Oh, yes, this is a good question. This is a great question. So Genesis' question is, if you lift weights up and down, why do you get tired? Because in the end, all the energy comes back to you, right? You put it in, take it out. Put it in, take it out. Put it in, take it out. The problem is that we are not good at receiving energy. When we do work on something, we burn very fresh calories. Calories are a unit of energy. We are taking food energy and turning it into mechanical energy and doing work on the weight. When we go the other way and the weight does work on us, the energy goes back and we do not recreate food. We don't deal with it well at all. We grind it up into little bits. That energy coming in, we grind up in little bits and distribute it randomly through our cells, and that is known as thermal energy. It's random energy. It's messy stuff that we can't do anything with. And we get hot. So the energy's there, but it raises our temperature rather than recreating useful stuff. And that's the problem. We're terrible at receiving energy. And so the same thing happens when you're climbing, when you climb up a hill, steep hill, you go mountain climbing or something. On the way up, you're turning food energy into energy associated with, ultimately with lifting yourself high. It's complicated because you have various parts, and so it's like your knee doing work on your thigh and so on. On the way back down, the energy is coming out of the energy associated with being up high, and it's going into thermal energy. And doing that, first off, turning it into thermal energy is not easy, and then dealing with it is not easy. Turning it into thermal energy involves stuff in your knees that you can hurt yourself coming down a hill. You may well have noticed this, that it may be more tiring going up a hill, but you're more likely to hurt to pull muscles and stuff trying to lower yourself. Take that energy back in and into your knees, for example. Is that okay? So, yeah. Is pushing something downward considered work? Yes. If you push it downward and it moves downward, you are doing work on it. You might think, well, that never happens because it's going to fall, right? Well, if I just let go, that's falling. If I do this, okay, that wasn't falling anymore. Gravity was pulling down on it, and I was pushing down on it too. So during that descent, I was pushing down on the ball. As it moved down, I was doing work. The result is it was picking up speed faster. It was carrying energy in the form of its motion. Extra. Yeah. Is that okay? And you can watch yourself doing this in 1,000 contexts. If you push on something and it moves in the direction you push, you are transferring energy to it. And that energy is either being eaten up by something that makes the story boring, like this. I'm doing work on the scale, but nothing much is happening. Why? Because friction is just chewing up that energy. But if you throw a ball horizontally, so gravity is really not part of the story, how do you do it? You start with the ball motionless, and you push it forward, toward the right, in this case. And you chase the ball. The ball begins to move, and you continue to push it. And it goes faster and faster and faster, and then eventually it gets out of your grasp, and then you can't do work on it anymore. But a person throwing, a pitcher, so I was talking to people in the softball team, whether you're throwing overhand or underhand, if you want the ball to go as fast as possible, and therefore carry as much energy as possible in its motion, that energy is called kinetic energy, incidentally, just to stop being vague. To put as much kinetic energy as possible in the ball, you want to push on it as hard as you can, and you want to keep pushing for as much distance as possible. Therefore, it's very hard to put a lot of energy into the ball if you're not willing to even move your wrist, right? No distance to work with. I don't care how strong your wrist is. You can push hard, but not for very much distance. But this is why pitchers, I'm certainly not an expert pitcher by any means or even watched enough, but Major League pitchers are all doing this stuff where they're way back here and then they're way out there. They want that distance. Okay? All right. So some details about energy. Energy has two principal forms. One of them is really in the motion of something. It's associated with actually moving. And the other form, so it's called kinetic energy. The other form, in conceptual form, is potential energy. And potential energies are all energies stored in forces, in the forces between things, within things. Gravity being an example, a spring being another example. So an object that's moving definitely has energy. The energy is associated with its motion. Just to give you a little insight into that, the energy that an object carries, for example, me, the energy I'm carrying, turns out to be half my mass times my speed squared. Velocity it's speed as opposed to velocity. Why? Because the direction part doesn't matter. I can carry the same kinetic energy going left as right, right as left. So what are the points that matter here? The more mass something has, given it is moving, the more energy it carries, and its proportional mass. That's not surprising. Two people moving together at the same as one person, it's not surprising that they carry twice as much energy as a team, as they do individually. Why speed squared, and what are the consequences of that? The speed squared part comes about because one way to look at it is the act of investing the energy in, for example, a ball. If I double the speed of a ball, I'm a pitcher, okay? And I pitch it slow, I pitch it fast. To pitch it twice as fast, that means that I have to either make it accelerate twice as quickly with twice the force, or I have to make it accelerate as before, but for twice as long. So to get up to higher speed, you have to either push harder or you have to push longer. Well, if we watch the active pitching, it's easy to push when the object's motionless. And the amount of work, I'm sort of have built the story right. Let me get it up to speed 1, and then I'll get it up to speed 2. To get it up to speed 1, I'm going to push the same the entire story. I push on it, and 1 second happens, and during that second it's moving, and I get to this location by the time I've managed to bring the ball up to speed 1. Now I want to get up to speed 2. Well, the ball's moving. I have to chase it and keep pushing it as hard as before, and during that second period of time, maybe the second, it will have traveled a lot farther. So during the first second in which I got it to speed 1, it didn't move very far. In the second in which I got it up to speed 2, twice the speed, it moved a whole lot farther because it's moving. It moved at the start and moved faster at the end. Well, so far is that okay? The idea that I'm pushing it, the faster it's moving, the farther I have to chase it to push it, to keep pushing. Let's look at the work you did. In the first second, you didn't do all that much work because it didn't move very far. Force times distance. But in the second, you had to do a whole lot more work because it's moving fast, and you had to chase it. It traveled 3 times as far in the second. You did a whole lot more work on it. The long and short of that then is, the faster you want the ball to move, the more work you have to do on it, and it goes up fast. It's not just proportional, it goes as a square. If the details on that don't make sense or don't stick, here's the upshot of it is, that if you compare 2 things, a bicycle moving at 10 miles an hour and a bicycle moving at 20 miles an hour, same riders, well, the bicycle moving 20 miles an hour carries 4 times as much energy in its motion, 4 times as much kinetic energy. You don't want to get hit by this thing, or you don't want to be that driving into a tree to avoid a squirrel, okay? That 4 times as much energy means it's 4 times as capable of doing things you don't want to have happen. So speed kills, which is some crazy drug war comment. It's true. The faster things are moving, the more dangerous they are, and it goes up fast. Okay, so energy stored, what I'll finish with in this is that energy in the motion, the kinetic energy, is easily seen. It's there in the capacity to do work. Energy stored in forces is more subtle because it doesn't necessarily involve motion. For example, this ball on the floor here has very little of a certain important kind of energy, and I'm going to do work on the ball, lifting it up. I'm pouring energy into it, and now there it is. It was motionless on the floor. It's still motionless. So it has its kinetic energy is the same as it was before. Nothing. And yet it has more energy. Where's the energy? It's stored in the force of gravity between the ball and the earth. I have pulled the 2 of them apart by a certain distance. I've stretched the force of gravity like a spring. Not quite like a spring, but that's the idea. It's now chock full of energy. It can do things it couldn't do before. For example, it can turn that energy back into kinetic and make the ball go fast, and so on. So we'll look down the road at various ways in which energy can be stored in forces. And to leave it with the ramp, what the ramp is doing is it's allowing you to invest the energy, the potential energy known as gravitational potential energy, in a wagon, lifting it up higher, stretching the force of gravity. It's allowing you to invest that energy in a way that's more comfortable and practical for you by way of small forces, but for longer distances. All right, so we'll leave it. Have a nice weekend and see you on Monday.